Hi, this is the third lecture on the dual active bridge converter. We looked at operating principles and converter design in the first two lectures. Today we're going to talk about PWM control and some topology variations. So the dual active bridge converter has some limitations also. If the input and or the output voltage vary significantly, then the ZVS load range is limited, so we don't get ZVS at low loads, and the load range for which we get hard switching keeps on increasing. Also, the RMS currents in the transformer and the switches, they are also very high at low loads. The transformer core loss also remains high at low loads. We're not doing anything to reduce the transformer core loss. So these factors can be addressed by introducing PWM control, which is what we're going to talk about next. And the other topic that we're going to talk about is the multipole DAB after PWM control. So this is the same circuit of the dual active bridge. Now what we're going to do is utilize one more flexibility in the switching of the switching sequence of the switches. And what we're going to do is, instead of getting square waves for the primary and secondary voltages, we can introduce instead of a square wave, a quasi square wave on one of the bridges. So either VP or VS can be a quasi square wave. And from implementation point of view, it's straightforward. What you do is you introduce another phase shift between S1 and S3, and that's what gives you this square wave, this quasi square wave. So what have we done really? What we are trying to do is, when we did not have this additional phase shift alpha p, then these two edges were aligned and these two current vertices were similar. So what we are doing by introducing this phase shift is increasing the value of the current at the point where S4 switches, and what that does is, in turn, it increases the value of the current at which S1S and S4S switch. This is going back to our reasoning for achieving zero voltage switching. We want this current vertex to be greater than 0 to achieve zero voltage switching for the secondary side bridge. And to help with that, what we are doing is separating the transitions for S1 and S4. And we have a converse case when we separate the transitions for S1S and S4S in the picture on the right side. So for m less than 1, when we were starting to lose zero voltage switching for the secondary side bridge, then this extra phase shift between S1 and S4 is actually going to bring some of that zero voltage switching capability back for the secondary side bridge. And for m greater than 1, by introducing a phase shift between S1S and S4S, we are actually regaining some zero voltage switching capability for the primary side bridge. We can go through the algebra, derive the current vertices, and then compute power going out of each bridge, out of one of the bridges over 1/2 switching time period, and come up with this value of power transfer, these expressions. So here the expressions have been arranged to again to expose some important features. So if you see this part of the expression is the same as what we had earlier. So so what we are essentially doing is changing the power transfer by this quantity, negative alpha square divided by 4 pi. Essentially we are reducing the power transfer capability of the converter to some extent. And also there's a subtlety in the power transfer. Now you get different modes of operation, so depending on the two phase shift values, now the phase shift between the primary and secondary bridge, and the phase shift that you are introducing between the two legs of the same bridge. So depending on the relative values, you get either this expression, the first one, or the second expression. So this one happens at lower power. The second expression, phi f times 1 minus alpha by pi. Phi f here is now defined as the phase shift between the fundamental components of the voltages on either side of the transformer. So fundamental component of this quasi-square wave and the fundamental component of this square wave, phase shift between those is what this phi f represents. Now just from a control point of view, we are still looking at phi f, the fundamental component phase shift, as a control variable, and this additional phase shift is just acting like a disturbance, or something that's modifying that equation, and we can actually compensate for that in our control just by using a feed forward. We can approximate the system again by the fundamental component of the square waves and the impedance at the switching frequency, and derive the power transfer, which is very similar to what you get with this with these exact expressions. Now we said that we are gaining some zero voltage switching range. How exactly would we choose the phase shift that we introduced to get the extra ZVS range? So now we have, instead of 2 current vertices, we have 3 current vertices. So if we go back to this slide, so we have 3 current vertices, and we have 3 different conditions for ZVS of S1 and S2, one condition for ZVS of S4 and S3, and one ZVS condition for all of the secondary side bridges, in this case for m less than 1. Okay, so if we rewrite the conditions in terms of this extra phase shift that we introduced, alpha p, then the expressions come out to be like this. The important thing to note here is that S1 and S2 always have ZVS, and there is a trade-off between getting ZVS for the lagging leg of HB1 and increasing the ZVS range for the secondary side bridges. So increasing this phase shift alpha p gives us gives us a higher range for ZVS of S1S through S4S, but when we start increasing this alpha p, we start losing the ZVS capability in the lagging leg of HB1. One compromise here we can make is to equate alpha p equal to this quantity here, and if we do that, then both HB1 and HB2 have 0 voltage switching as long as this quantity phi is greater than 0. And if we now look at what this implies, alpha p equal to 1 minus m times p, this is nothing but equating the volt seconds across the two sides of the transformer. So for m less than 1, VDC1 is higher than VDC2 prime. And what we are doing is introducing a duty cycle control for VP, so that the average voltage applied across the transformer on the primary side is now equal to the average voltage that we are applying across the transformer on the secondary side. So the duty cycle that we are introducing for VP times VDC1 is equal to VDC2 prime, that is VDC2 reflected to the primary side. So that's what gives us the soft switching for extended soft switching for both HB1 and HB2, all of the switches, and we can derive similar conditions for the case when m is greater than 1. So the output voltage reflected to the primary side is greater than the input voltage. When we use these conditions for the introduced phase shift, and we now plot the ZVS boundary, this is what we see. Without PWM we had the green boundary, with PWM we have the blue boundary. So you can see that when m is close to 1, that we are not really gaining much, but as we go away from 1, if the input and or output voltage is varying significantly, then we start gaining quite a bit in the ZVS range. The increased ZVS range is not the only benefit we get by introducing PWM. So how do we choose the PWM duty ratio in order to minimize RMS currents? We can go back to our 2-bus system where the voltages on the AC bus are fundamental components of the square waves we are applying on the two sides of the transformer. So we have these magnitudes and phase angles for the voltages. Now the magnitude for the primary side voltage is being modulated by this cosine of alpha p divided by 2 because we are now introducing duty cycle control for the primary side bridge. You can look at this problem similar to the case of the 2-bus system, where you're trying to minimize RMS current in the line for a given power transfer level. So we can write down the equation for the fundamental component of the current, and then minimize the RMS value of this for a given power transfer level. So power transfer level is given by the second equation. Keeping this constant, we can minimize I1 RMS and find out what value of alpha p gives us the minimum value of I1 RMS. So after you go through that exercise, will come up with this value of alpha p, and um, this is not simply equating the the reactive part of the current to 0. That's just one thing to keep in mind. An illustration of this minimization of the RMS current is shown for a specific design in these two plots here. So we have different ways we can choose the value of alpha p, and here I've plotted 4 different ways that you might choose alpha p and see its effect on the RMS current. And this is being plotted for the no load condition. So at no load, what is the RMS current in the transformer for different choices of duty cycle. If we go with the scheme in which we are equating the volt seconds across the transformer, so that's this green curve here for alpha p, then we come up with the green curve here for the RMS current value. If we choose alpha p according to this equation here, then we are getting this red curve. If we include not just the first harmonic but also include the third harmonic and minimize the RMS current including the third harmonic, realizing that we have power transfer again constant given by this equation, then we have this black curve. And if we do a numerical minimization for the RMS current, then we have the blue curve. So you can see that there are different ways we could choose alpha p, and if you just go with the volt second equalization across the transformer, then we may not get the absolute minimum value for IRMS, but it does reduce the RMS current quite a bit compared to the case without any PWM control. The PWM control also helps in reducing the transformer size. So the transformer size primarily depends on this product here of the maximum volt second product and the RMS current in the transformer. Without PWM then we have maximum volt second equal to this expression, and with PWM control we are actually able to eliminate this factor of 1 plus M max over 2. So the factor due to variation in the input or output voltage is actually eliminated from the transformer size calculation. Just as an illustration, if we had a variation of 0.5:2 in M, then the ratio of these two expressions would be 1.33, and you would end up reducing the core area requirement by 33%. So transformer size would reduce by 1/3 just by introducing PWM control. Now we talked about doing PWM for one bridge so far. We could do duty cycle control for both the bridges, and instead of having square waves at the transformer primary and secondary, we could have quasi square waves at the primary and the secondary of the transformer. Now This leads to different modes of operation in this converter. There are in all 5 different possibilities depending on the relative values of the phase angle and the duty cycles that you introduce for the two voltages on either side of the transformer. It turns out that of all these 5 modes, only mode 3 and mode 4 are actually useful. Mode 4 is useful when we have M less than 1. So if the primary referred VDC2 value is less than VDC1, then mode 4 is useful only at low powers. Mode 3 is useful when when M is greater than 1, and again it's useful only when when the power transfer level is quite low. We can analyze these waveforms, derive the current equations, and then use those current values to derive the power transfer, and we can come up with these expressions for the exact power transfer to the converter. We can also approximate this again by the fundamental component, and if we do a comparison, it's pretty close, with some exceptions, particularly for mode 1B. I'd rather skip that detail, but you can look that up in one of the references which talks in detail about PWM control. So I said that mode 4 operation is useful at low power. If we look at the waveforms in detail, the current waveforms in detail, we'll find operation to have this kind of current waveform. And the important thing to note here is that we actually have two zero crossings for the inductor current in each half cycle. So between this point and this point, the inductor current goes from negative to positive here, and then goes from positive to negative again here, and then once again goes negative to positive at this part. So we're getting two zero crossings going from negative to positive, and this is required to obtain zero voltage switching for all the switches. So because M is less than 1, we are looking at zero voltage switching for the secondary side bridge, which is what gets compromised first. Now the turn on instance for all the switches are indicated at the bottom here. So for S1 to have zero voltage switching, we want this current vertex to be less than 0, or ID here to be greater than 0. For S1S to have zero voltage switching, we want this current vertex to be greater than 0, so IB greater than 0. For S4S, again we want this current vertex IC to be greater than 0. For S4 we want this current vertex to be less than 0, that is IA greater than 0. Now we can enforce those conditions just on these current expressions and get zero voltage switching. However, we also have to look at the RMS currents in the transformer, and we want to minimize that so that the loss due to the RMS currents is minimized. So so the thing that we note from these current waveforms are as follows. in this middle graph, there are portions of the current waveform which have a light gray area under it. This is the portion where the primary side bridge is actually freewheeling. So so there is zero voltage across the primary of the transformer between this point and this point. So there is no power being transferred from the primary bridge to the transformer in this time period. So so all of this current is actually giving us just loss. So we want to minimize IB and IC, but to get zero voltage switching we still want IB and IC to be greater than 0. Also we want to make sure that IA is as close to 0 as possible, because we don't want loss in this part of the current waveform. The area which is shaded with dark gray, that is the part in which some power is being transferred first to the first from the transformer back to the bridge, and then being transferred from the bridge to the transformer. So this entire area which is shaded in dark gray, this is resulting in zero power transfer. What is actually giving us positive power transfer is this unshaded area, which is between these two time instants. So to keep the RMS currents low, we want to bring IB, IC down towards 0, IA up again also towards 0. But to get zero voltage switching, we want IA, IB, IC to be all greater than 0. So that gives us the limiting condition on achieving zero voltage switching and minimizing the RMS currents. So if we just equate IB, IC and IA to 0, we come up with these expressions for alpha P and alpha S, the freewheeling intervals for the primary and the secondary side bridges. And this choice now gives us zero voltage switching down to 0 load. It minimizes the RMS currents, and also now that we are reducing the volt second across the transformer, and as we go to 0 load, then phi f goes down to 0 load, so alpha p and alpha s both go towards pi. So the volt second across the transformer also go down to 0, so the core loss in the transformer also goes towards 0 as we keep going down in load. So this choice of the freewheeling intervals, it gives us all the three benefits: zero voltage switching down to 0 load, minimized RMS currents, and also reduced core loss at low loads. We said earlier that the dual PWM is useful only at very light load conditions. So what happens is that we can start with dual PWM at light load conditions, then transition to the single PWM that we talked about earlier as the load increases. The transition point occurs at this value of phi f that's indicated here. And we can come up with a composite scheme which will have a seamless variation in alpha p and alpha s, starting from phi equal to 0 all the way up to phi equal to pi by 2. This is the kind of power transfer you get with the composite scheme. It's the blue curve indicated here. So we started with the black curve without any PWM control. We introduced single H-bridge PWM control, which gives us a red curve. Now we introduced dual PWM control and a scheme to transition from dual PWM control to single PWM control, and eventually to no PWM at the maximum phase shift, maximum value of Phi-F. So at Phi-F equal to 90, we don't have any PWM control at all. So that helps us regain all the power transfer capability of the converter also. So if you remember, we said that with single PWM control we were actually losing some maximum power transfer capability. So the difference between this point here and this point here on the red curve. The right plot compares the RMS currents in the converter as the power transfer is increased from 0, and you can see that for the composite scheme we are able to get theoretically 0 current at 0 load, and it is increasing slowly, and then it merges with the black curve at high power levels. Here are some experimentally measured data. So the left set of plots is for a converter operating with 600 volts on the input, 300 volts on the output, and you can see that with the composite scheme we are able to minimize the RMS currents, and we are able to get a significant boost in efficiency, somewhere from in the 25% region to about 78% region at really low loads. The gain is actually lower when VDC2 is higher, so we are getting closer to M equal to 1. So like we discussed earlier, PWM helps only if you have wide variation in the output voltage or input voltage, and that's illustrated here, but we still get a significant benefit in terms of RMS current reduction and efficiency boost at low load. So that concludes the discussion on PWM control. The dual active bridge converter can be extended to multiple number of ports, so it could be viewed like a power system where you have multiple voltage sources which are separated by inductive lines. So in the two bridge case we just had two voltage sources separated by one inductance. If we have a 3-port transformer, then we can think of 3 voltage sources, each realized by an individual H bridge, and then these are connected to each other by the leakage inductance of the 3-port transformer. Now the power flow in this system can be analyzed using just fundamental component analysis, and and the challenge here is that we want to minimize circulating power flow. So if we want to transfer power from V1 to V2, then we don't want power to flow from first V1 to V3 and then V3 to V2. We'd rather have power flow directly flow from V1 to V2. So this is like a power system problem where we are trying to minimize circulating power in an interconnected power system, and we again have flexibilities over the phase angle of these voltages, and also the magnitude of these voltages, so we can introduce duty cycle control to control the fundamental component amplitude of each of the voltage sources. The dual active bridge converter was introduced with full bridges on either side of the transformer, but it is possible to have a similar operation with a half bridge also. So that you can use, instead of a full bridge to produce the square wave, you can use a half bridge to produce a square wave, similar to similar to load resonant converters. So here we are essentially replacing switches and adding capacitors, and we are losing some flexibility also. So now with the half bridge we can only impress a square wave at this winding. We cannot get a quasi square wave, so we'll lose PWM control flexibility on the side that we replace with a half bridge, but we'll save on the number of active devices. And that is the end of this lecture. So we looked at PWM control in quite some detail, and I briefly indicated different topology variations for the dual active bridge converter. There is a list of references I've provided. Some of them talk about the initial development of the converter. Some have details on the on the converter design, particularly this reference. This is a very good reference for converter design. There are some empirical comparisons done for this converter compared with other possibilities for bidirectional converters. Then this reference is a good reference for small signal modeling of the converter. So I encourage you to go and look at these references, and also look at some recent papers on the dual active bridge converter. This converter has become very popular recently because of its simple structure and a simple mechanism to effect bidirectional power transfer between not just two DC buses, but even for multiple DC buses. So so I think it's a very good topology. It relies on some very basic fundamental principles, and it provides a lot of benefits for for converters which require bidirectional power transfer. And that is the end of this lecture. Thank you.